So we now come to the main event of the afternoon, the talk by Jim Anderson, who is receiving the Camille and Henry Dreyfus Prize in Chemical Sciences for Environmental Chemistry for pioneering measurements of the free radicals that drive the chemistry of the atmosphere, establishing the foundation for worldwide agreements to protect the stratospheric ozone layer. Jim has had a 45-year career at Harvard. He earned his bachelor's degree at the University of Washington, followed by a PhD at the University of Colorado, a postdoc at Pittsburgh, a short faculty stay at the University of Michigan, several years, before joining the Harvard faculty in 1978, where he has been, as I said, for 45 years. What characterizes Jim's work for me, a non-expert, is the innovation and the command of various tools necessary to understand this diverse subject, from chemical instrumentation for spectroscopy, lasers, optomechanical devices, other kinds of optics and spectroscopy measurements, as well as tools that a nanotechnologist like me never thinks of, such as drones or high altitude aircraft or long duration flying vehicles to acquire the samples necessary to do this. So it's a real pleasure to give the stage over to Jim Anderson to present his award lecture to us.
Frank, and move over so I can see the screen as well. And I have to say, thank you, Matt, for that, but the Dreyfus Foundation represents the remarkable insight in coupling education at all institutions, all universities and colleges in this country, in a way that's truly unique. At the same time, developing new postdoctoral programs at the cutting edge of problems that are immediately of concern to all of us. And I think the leadership that's intrinsic to the Dreyfus Foundation is something that I find remarkable, and that it gives tremendous meaning to this award to me, and I profoundly appreciate it. I want to express that. Well, we've had a remarkable range of discussion today. I think the complexion and the way in which this series of presentations was put together was, again, a reflection of the insight of the Dreyfus Foundation, and I enjoyed these talks immensely. Mine's going to stray somewhat, and the basis for this is my profound concern about quantitative forecasts of risk going forward, and I pick a number of different. This is probably the weakest laser I've ever encountered, and I'll try to move it very slowly so it actually has some effect. So we want to look at the issue of glacial disintegration that Dusty so profoundly represented this morning. We also want to look at forecasting wildfires and agricultural drought. We also are extremely interested in this large-scale Brewer-Dobson circulation of the atmosphere, because subtle shifts in that affect not just the north-south position of the jet stream, but also the amplitude of oscillation that gives us this tremendous variance that we can all see already in the climate system. But it also reflects shifts in drought areas that trigger water shortages and food shortages that again trigger refugee flow. And the forecast now is 200 to 250 million by 2050 that are driven out of their homeland by the lack of water and food. But we don't have the quantitative forecast to actually pin that down. And then there's the issue of severe storms and hurricanes, and the way in which those storms are dissected for forecasts over the next week, 2 weeks, is one issue, but also the way changes in the larger scale dynamics of the atmosphere affect the intensity and frequency of hurricanes is a huge problem. And of course, this is all a result of the forcing by the use of fossil fuels, the increasing CO2 and methane. And then finally, this coupling between the intrinsic dynamics that's brought about by added water vapor that is the gasoline that fuels the remarkable convective injection uniquely over the United States in the summer. And the way in which the coupling between this dynamics and the catalytic chemistry act requires the kind of diagnoses that we don't have yet, because we have to have those extremely high spatial resolution observations in all of these aspects, whether that's in situ or remote. And that's the subject I want to talk about. So the context for this and the background was actually articulated beautifully in this new National Academy of Sciences report, Global Change Research Needs 2022 to 2031. And in the executive summary, this report, this National Academy report, pointed out this explicit focus on risk, namely that traditional climate research is not meeting decision makers' needs. Moreover, the committee recommends that the U.S. prioritize research related to managing climate risks. The global climate models or Earth system models have limited ability to simulate local scale climate that inflicts societal harm. And it's the recognition of the failure to provide the observations that are necessary to establish the physics that's controlling these systems that is the problem. And so the ramifications, of course, immediately affect the inability to quantitatively navigate risks, drives an inability to do econometric calculations. And if you don't know how rapidly sea level is going to rise and the financial impact on that, you can't do an economic calculation. But it's the economic calculations that drive public policy changes. And we found that with the Montreal Protocol and the ozone problem, that until you unequivocally pin down the scientific cause, you can't instigate the critical societal objective of public policy change. And then finally, the climate change and intergenerational justice, this issue of what are we leaving to our children and grandchildren. So here's I'm going to just pick off the last 3 weeks of what's come out here. And one of them is this recent NOAA report that actually goes through and carefully looks at the billion-dollar disaster events in the United States alone from 1980 to 2021. And it's now reaching $500 billion a year. But you notice whenever you've seen an exponential growth, that's exactly what you're seeing here, with a doubling time of about 10 years. And we all know that the onset of these billion-dollar events, whether it's flooding or wildfires or whatever, that wasn't forecast. We've observed these because Mother Nature has delivered them to us, not because we knew they were coming and we forecast them. This is entirely outside of the ability of the current scientific structure to forecast these events. Yet when you're talking about a $500 billion a year impact, it becomes critically important. So again, this was not quantitatively forecast. And if you were sitting and you were a secretary for the planet, Secretary of Defense, Secretary of the Treasury, they have clear responsibilities, and their failure to operate correctly is directly fed back to them, to put it gently. If we had a Secretary of the Planet, we would never be cruising along without this kind of forecastability. And this is something that is fundamental to the failure of the system. So here's another news event. Increase in sea level rise predicted by 1 foot set this whole process into catatonic seizure. And Dusty beautifully laid out the way in which you can dissect these glacial systems, but it turns out that the uncertainty by 2100 in the degree of sea level rise has huge impacts. It almost doubles the impact over everything else on global GDP because of the serious nature that it brings. The other news event that came out that simply underscores a critical problem are these delicate glacial systems, both in the Andes in South America and also in Tibet. The entire spine of the Andes has these small glacial systems that feed the entire agricultural system during the growing season. And they are absolutely essential to the fundamental lifestyle of all of South America. But it's also true of the Tibetan glacial structure. It feeds 75% of the water to China, 90% to India, and a dominant part to Southeast Asia. And yet these glacial systems, because they're so much smaller than Greenland or the West Antarctic, are absolutely essential to understand in terms of the rate at which they're disappearing. And then this New York Times article that came out again about 3 weeks ago, this Western drought that we're seeing now, it turns out it's the worst drought in 12 centuries. And that's a cause that's driven by the large-scale dynamical structure of the atmosphere, where the northern shift in the jet stream moves the climate of northern Mexico into the southeastern part of the United States. So this isn't a fluctuation that's going to go away. These large-scale dynamical shifts are permanent. Okay, and then of course wildfires, and this headline just happened to point out that it's really the creation of the financial instabilities in the financial market that leads to instability in societal structures. And this is a crucial part, and we need to solve this problem. So I don't have to tell this audience this fundamental principle, but it's amazing how many audiences I do have to point it out to, and that is a fundamental principle in the physical sciences, that a quantitative understanding of the coupled mechanisms that control the response of a given system to external forcing requires high spatial and temporal resolution, three-dimensional dissection of the coupled variables within that system. Moreover, the simultaneously observed within the same volume elements is crucial for all these major climate subsystems. Until you can dissect the Jacobians, if you will, of the coupling within these systems, you can't understand the physics, nor can you understand how that system is going to respond to external forcing. And that's a basic principle that has to be carefully watched. And I stole all of this from Dusty. It's just this magnificent example of the multiple variables for dissecting glacial dynamics, all the way from the topography, the bedrock, through the glacial flow, the history, the end glacial water storage, the resolved three-dimensional ice flow velocities. All of these things have to be observed with very high spatial resolution inside the system. And as Dusty pointed out, this hasn't been done. And that is a crucial problem. So if we look at, we'll just quickly go through these priorities: tested and trusted forecasts, sea level rise, tested and trusted forecasts of wildfire risk, but also drought, crop loss, water supply loss, and how that's linked to fossil fuel use. I mean, it's remarkable how rapidly the desecration of forest systems in the western part of the United States came on. But it's also true in Australia and Siberia now, the same issues. This one I've already beaten on, and that is this question of the large-scale dynamics, where I'm plotting the equator here on the right, moving over to the pole on the left against altitude, and the separating line between the troposphere and the stratosphere is shown here. But this overturning circulation is controlled by very subtle wave breaking and downward control, But none of that has been tested observationally. There's beautiful theoretical work on this, but until we understand exactly the quantitative aspects of those mechanisms, we can't determine how this is going to change with increasing forcing. And again, this gets back to not just the position of the jet stream, but the loss of western to eastern discipline that produces these very large amplitude wave structures that draw cold air down from the Arctic, and then all of a sudden that cold air strikes moist air coming up from the south, and that's what creates these storm systems. The dissection of large-scale severe storms, and in particular here, the flooding events, when you look at the destruction that emanates from the flooding events, it's increased remarkably. A big part of that $500 billion a year comes from this process. And then finally, this almost demonic coupling between dynamics and chemistry, but just over the central United States. This doesn't occur anywhere else on Earth, and it's caused by the warm inflow of moist air from the Gulf of Mexico with a very rapidly increasing surface temperature that drives an exponential increase in water vapor. A low level jet carries that over the central United States. But interestingly, what triggers the convective injection are gradients in the moisture of the soil. That's what executes the overturning event that starts to release the intrinsic energy contained in the vapor, and you have this explosive upward drive that inserts water vapor directly into the stratosphere, except it triggers exactly the same chemistry that Frank was talking about that occurs over the Antarctic and the Arctic. But more than that, the North American gyre, the anticyclonic gyre, traps this injected material and turns it into a batch reactor. And this is a critical problem that then couples climate change into ozone loss, but not in the polar regions in the winter. This is over the central United States in the summer. Okay, so without tested and trusted quantitative forecasts of risk, it's not possible to calculate the economic impact. When you don't have a trusted economic calculation, you profoundly compromise the possibility of effective public policy change. So the trace here is establishing the physics that's controlling these climate systems in order to develop the foundation for tested and trusted quantitative forecasts of risk to then drive public policy. So what we need is a new way of achieving these very high spatial resolution and temporal resolution observations of all of these climate subsystems. That's what has not been developed. And when you think about why that is, it's really tied up in the development of tendencies of government systems to pick certain approaches, and I think satellites are an example, and satellites are very valuable, but there are limitations. And so when we look at the objective of developing a new climate observatory, the stratosphere turns out to have remarkable capabilities. Namely, it's dynamically stable in the stratosphere. The absence of weather means that quantitative solar radiation is simple and reliable, but it's also very close to the target. It's only 20 kilometers or so above the surface. And that turns out to be extremely important. So this is a technology that, as many of you know, I've been working with John Langford for years on developing solar-powered stratospheric aircraft. And we thought we had the solution. Boeing had purchased Aurora Flight Sciences, which was developing this. But along came the 737 MAX problem. Boeing cut all new technology, including the solar-powered stratospheric aircraft. But on the other hand, that's probably the best thing that ever happened to this project, because the rapidly evolving electrochemistry gave us energy storage that went from 200 watt hours per kilogram to now 600 watt hours per kilogram. And this new aircraft design has a wingspan of 35 meters rather than 80 meters for the same scientific payload. And when you reduce the wingspan of a structure like that, it's not just a matter of reducing the cost, it's a matter of building resilience into that observing system, which we now know we have. So the first of these aircraft is now under construction. The first flight should be in September. That won't be a flight into the stratosphere yet, it'll be the flight of the system. So these aircraft then have a flight duration uninterrupted of 12 months in the stratosphere. And this is really part of the crucial aspect of dissecting these systems. You have to observe day in, day out, week in, week out, relentlessly to establish the coupling of the variables within these systems. It'll reach altitudes of 85,000 feet, which means you can get to a height to dissect with in situ measurements this large-scale dynamical overturning structure, and the instrumentation specific to the selected climate target. So we're looking at multiples of these, each with the right instruments to attack the specific problem within that climate subsystem. And of course, along with this, there are rapid developments now in laser systems, LiDARs, radars, nanoelectronics, photonics, quantum devices, robotic systems. The miniaturization that's come along just in the past 2 or 3 years for sophisticated observing systems has been remarkable. And it's a huge help here because mass is a very important aspect in the strategy of this. So consider how this observing strategy complements satellite observations. I just point out that for many of these high spatial resolution observations, you lose signal as the square of the distance between the observing platform and the target. So if you're at 500 to 800 kilometers in the satellite and you come down to 20 kilometers, you're gaining orders of magnitude in that return signal. Second thing is the satellite in low Earth orbit is moving over the ground at 8,000 meters a second, whereas this observing platform is moving at 30 meters a second. And that turns out to be extremely crucial for getting these high spatial resolution observations in 3 dimensions. The next aspect is that we operate below the ionosphere. And of course, the ionosphere eliminates large segments of the electromagnetic spectrum for a satellite, but we're below the ionosphere, so we have no interference from that. And then finally, this key aspect, and that is that a majority of these unsolved, unresolved problems in climate research are actually confined, to very limited geographic regions. I mean, you look at Greenland, that's 0.5% of the area of the Earth. The Antarctic, Western wildfires, again, well less than 1% of the area. There are hurricanes, agricultural drought, methane release, and so on. So these regions are much less than 1% of the Earth's surface, yet they're driving the fundamental changes in this climate structure. Well, a satellite spends much less than 1% of the time over a specific target. It's also 500, 800 kilometers away, moving at 8,000 meters a second. That's not how you design a system to dissect things with high resolution. But the the observatory in the stratosphere spends 100% of its time over the target. But importantly, the trajectory is set specifically by the tailored flight algorithm determined by the instantaneous observations made by the instruments on board. And as you could see from Dusty's talk this morning, even when you start with 0.5% of the area, for example, of Greenland, there are areas within that 0.5% that are crucial for the rate of disintegration of those ice systems. And this allows you to focus exactly where you need to spend your time. And then the instruments, again, on each platform are designed specifically to attack the scientific problem. And by the way, the observation platforms here are actually quite inexpensive. I mean, we're looking at 24 or more of these, but the cost per aircraft is not a large factor in this consideration. Okay, so then I'm just going to finish up by reiterating the problems. This issue of the large-scale dynamics is right at the top of the list. And the sets of measurements that are required to do that are in situ measurements of these tracers, SF6, methane, N2O, CO, CO2. The measurement, in situ measurement of flux divergence for many of these problems is absolutely crucial for the dynamics. The very short-lived halogens, the way in which convective injection comes into the stratosphere through stratotropic exchange and then is distributed, is a brilliant, easy way of tracking exactly what those dynamical structures look like. And then, of course, water isotopes and water phases, another example. But you can also map the three-dimensional velocity fields and the fluctuations in those for the wave breaking that's driving the downward control that ultimately controls the overturning rate of this system. None of these measurements have been made. For the issue of wildfires, the question here is using, or the approach here is using radar systems, first of all, to map the upper 50 centimeters of soil moisture. This gives you a 2 to 3 month head start on knowing where those wildfires are going to break out, along with LiDAR observations of canopy moisture. Those two measurements are absolutely essential for forecasting. And then, of course, because you can operate with such high spatial resolution, you can instantly detect the outbreak of a fire event itself. And then the issue of small glaciers and water vapor, running water for agriculture and so on from these glacial systems in the Andes and in Tibet. This is actually, compared to the difficulty that Dusty was talking about this morning, small glaciers are actually much easier to dissect because they're far more dynamic, they're much smaller, you don't have the depth of ice to deal with, but the intrinsic resolution and capability of ice-penetrating radar must be applied to these issues. And then finally, this gets back to the discussions we had this morning about aerosols and the control of shortwave forcing of the climate itself. And here, there's a major uncertainty, of course, in reflected light. And there are really two components to this. One of them is the cloud systems themselves. And when you look at the intrinsic complexity of the physics that's controlling that cloud formation, this is one of the most complex problems because these different cloud systems are very different in the tropics than they are at mid-latitudes, but they all require this combination of infrared sounding, microwave sounding, K and X-band radar observations, imaging polarimetry, and water vapor profiling in its various phases with LiDAR in order to understand what is causing the changes in this cloud structure. And then, of course, there's the issue of aerosols, not only their chemical composition, but the phase angle. When you're just 20 kilometers above the surface, you can observe the dynamic range in that phase angle in a way that is the angle between the solar illumination and the observing angle that's impossible by any other technique. Also, new optical systems are coming out that are tiny, but they can also detect polarization and also the chemical content of these aerosols. But you have to be in the proximity, and the aircraft can pin a specific point and follow it in a Lagrangian sense to look at the evolution in time that's taking place within those systems. That's absolutely essential information for the chemical analysis. And then this is a somewhat remarkable thing, and that is that, as many of you saw, about 4 or 5 months ago, it came out that the actual altitude looking at the impact of sea level rise, the actual altitude was off by hundreds of meters because the low resolution observations were looking at the top of the tree and systems rather than the ground. And so the solution here, of course, is to use LiDAR, and rather than a 2-kilometer resolution, you can get 10-meter resolution, and you can find out where that ground level actually is, which is so important when you're calculating impact for a given half-meter or meter of sea level rise. And then finally, this dissection of the actual chemistry requires that you follow the injection of water vapor and, in a Lagrangian sense, watch the time evolution of the chemistry that's taking place in that system. And just to show you, this is NextRad radar data that we use all the time now. And it just shows you the propensity for thousands of stratospheric penetrating storms that occur, but just over the central United States. If I showed you that plot anywhere else in the world, you'd see no accentuation in it. And so the United States is blessed by this remarkable convective injection that can trigger ozone loss. Okay, so to do that requires in situ measurements of radicals, reactive intermediates, total water, and so on. But again, the ability to do this in the stratosphere, in situ, at high spatial resolution is critical. So this is my last slide. I just want to say that the objective of this is, again, to develop these tested and trusted forecasts of risk, wildfires, sea level rise, irreversible shifts in the large-scale dynamics, the frequency of flooding, agricultural degradation, hurricanes, and also UV radiation. So that's it. Thank you.